Excuse me, class, ha? Okay, let me share my screen to you. We are now in module 2. Please inform me if my slide won't transition again, okay? So we are now on module 2 and we are on kinetics of homogeneous reactions. So the first part of this set of slides will be focusing on ideal flow, or the manner in which the fluid or the system inside your particular reactor contact each other. So ideal flow or contacting patterns for ideal reactors. We have 3 ideal reactors. We have the batch reactor, the constantly stirred tank reactor, otherwise known also as the back mix reactor or the mixed flow reactor. And the third one is the tubular reactor, known as the plug flow reactor. So these are the 3 ideal reactors. So for your batch reactor, there is uniform composition everywhere inside the reactor, but we expect, of course, as time proceeds, that the composition of the system will change. Now, as for the steady state flow reactors, so we have the 2. The one on the left is your plug flow reactor, or the tubular reactor, comparable to a pipe, that of a pipe. And in here, fluid passes through the reactor with no mixing of earlier and latter entering fluid. It's as if your fluid are on a straight line and no mixing will occur into this fluid elements or in any of the fluid elements. So there is no overtaking of these fluid elements, as if the fluid moved in a single file through your reactor. So the one I'm referring to is your plug flow reactor. So it's not transitioning again. Okay, so this is your plug flow reactor. The one on the right is our mixed flow reactor, or our constantly stirred tank reactor. Constantly stirred in the sense that we have the stirrer here to ensure that the contents or the system inside your reactor will be uniform at all times. So uniformly mixed, same composition everywhere within the reactor, and the composition of your system inside the reactor is the same composition of the fluid that leaves the reactor. Okay, so concentration A here inside the reactor is the same concentration A of the fluid that leaves the reactor. Now, for the rate law, it's very fundamental as to the understanding of kinetics, and as discussed in your FEChem, the introductory part of your FEChem. When we speak of the rate law, you have the rate expression on the left side of your equation, and it could either be negative or positive. In the sense here, you have it written as negative. As review, telling you that species A, the subscript here that appears in the R is the species in which the rate is based on. So meaning the rate of reaction is based on the consumption of this particular reacting species. I say consumption because it's a reactant, because of the negative sign that you are seeing here before the rate symbol, the negative R sub A on the left side of our equation. On the right side, you have the product of two terms. You have the rate constant, we call it the rate constant, K sub A, and you notice that it has also a subscript of A. So meaning, whatever is the species that was used as a basis in determining the rate of your reaction, that would be the same species that is used as a basis in determining the rate constant, K. So the rate constant as the term constant, so it's a constant. It's a characteristic of your particular system, but even though we call it a constant, it is temperature dependent. So when we speak of the same reaction, the same temperature, the value of such a constant, is fixed. However, if we change the temperature, this particular rate constant changes because, as I've said, it's temperature dependent. Now, what is being multiplied to this rate constant T or rate constant K as a function of T is a function which can either be a combination of several concentrations. So you can have the concentration of A combined to concentration of B to C and so on and so forth. It could be not as simple as the one you're seeing here, wherein you only have, let's say, multiplication of this concentration, but it could also be division of these concentration terms. Okay, so two terms appear on the right side of your rate law. The temperature-dependent term, which is your rate constant K, and the concentration-dependent term because it's, of course, in terms of concentration. These concentration terms, by the way, class, can also be raised to exponents. Okay, it can either be whole number exponents, fractions, or even negative exponents. So this rate law gives the relationship between the reaction rate and the concentration. So as you can see here, the reaction rate based on species A is being related to or correlated to the concentration of the species that appear here on the right side of your equation. Now, the K is the specific reaction rate as referred to in other textbooks, especially the old one. So right now, it's simply being referred to the rate constant, but some older versions of books on kinetics and chemical reaction engineering refers to it as the specific reaction rate. Now, according to Arrhenius, so its temperature dependency could be expressed in terms of this equation. So your rate constant K is a function of the temperature. You can see here the temperature and a function of the frequency factor A. In some books, this frequency factor A is represented as K sub O. So it has a subscript of O or 0. So in this formula, you have A e raised to negative E over RT. So E is the activation energy of your reaction and R is the universal gas constant. So the units of K, so your K can have a unit or it can have a set of units, and this A, of course, has to be the same. And they depend on the overall reaction order. Now, what do we mean with the overall reaction order? Now, in your, I'm not so sure if this was discussed in your Chemistry 1, as an intro to kinetics or in your Phy-Chem, but for example lang, you have, let me annotate, your rate law is written as K sub C sub A C sub B squared. So we know that your temperature, rather concentration terms constitute the product of C sub A and C sub B squared. The overall reaction order or the overall order of the reaction is the sum of the exponents of the concentration terms. So we say that in here, the overall order is 3. So you have 1 for C sub A and you have 2 for C sub B. So this is an example of a rate law. Or it could even be only having C sub A here, wherein your overall order is 1. If you don't have any concentration term here, your overall order is 0. And we say that our reaction is 0 order. Okay, so the temperature, again, the temperature is the determining thing in terms of the value of the rate constant. And this rate constant's set of units or unit is dependent on the overall order of the reaction as stated. Okay, so let me clear what I have in here. So far, do you have any questions in here? When you do your calculations later on, it's very important that you reflect the correct unit or set of units for this K. And as such, I am emphasizing that the unit or units for K is based on the overall reaction order. Now, more on the rate law. So for a reaction given, it's a hypothetical reaction. So you have species A reacting with species B, forming species C and D. And you have the coefficients of this as A, B, C, D respectively. This is the fundamental relationship as to the values of the rates in terms of the species that you are seeing. So the rate in terms of A divided by A is equal to the rate in terms of B divided by B, C divided by C, and D divided by D. This is true whether your reaction is said to be elementary or non-elementary. So as to when do we categorize a reaction as elementary or non-elementary, we will discuss it later as we go along. But this is very important. No matter how complicated, no matter how complex is the rate equation or the rate law of a particular reaction, the relationship of the rates are based on the stoichiometric coefficients that appear in the balanced chemical reaction. So the stoichiometric coefficients that I'm referring to are A, B, C, and D. Okay, so your reaction in the first place has to be correctly balanced. Now, another way of writing this class is you get rid of this negative sign here. So you notice I place the negative sign in here, and you can place the negative in here, denoting that A and B's are actually, or B are actually reacting species. That is why it's important that you place negative in here. And we have positive rates for C and D because they are products. Now, if we have this specific reaction on the formation of nitrogen dioxide, and we wish to relate the relationship between the rates in terms of NO, O2, and NO2, so this is it. So you see that NO, the rate in terms of NO, a reacting species divided by 2 is equal to the rate in terms of O2 divided by 1, also equal to the rate in terms of NO2, nitrogen dioxide, divided by 2. Okay, so this is in terms of the relationship between the rates of your reaction based on the species in your reaction. So the rate will be different if the species is different that was used as a basis. So it could be only the same if the stoichiometric coefficients of this species are equal in your balanced chemical reactions. Okay? Any questions? Okay. So as a little yes, there's a question.
None, miss, none.
Okay, so we go to a little self-test here. Okay, write the rate law for the elementary liquid phase reaction that you are given here. Okay, so we know from our Chem 1 and our introduction to physical chemistry that the way we write the rate law is based on the concentrations of the species that appear in your balanced chemical reaction. So their concentrations are raised to the exponent or raised to an exponent equal to the coefficient of this species that appears in your balanced chemical reaction. So the answer for A in this case is, so you have negative R sub A is equal to K, C sub A raised to 3, and C sub B raised to 2. This is how we write its rate law. Now, I missed to write here, your rate constant has to be specified that it is in terms of A. Why? Because your rate is in terms of A. If we change this to negative R sub B, negative still because B is a species, there's nothing that will change in terms of the concentration terms. It's still the same. However, your rate constant here will not be in terms of A, but rather in terms of B. So you will have now K sub B. Now, if it's in terms of C, if you express the rate in terms of the product C, then this will be now positive. So this is just one way of writing the rate law. Oftentimes, class, we always write rate law in terms of the reacting species. So if it's B, you write it like this. But in terms of the concentration terms, that would still be the same. Or in terms of the product C, that would be K sub C, C sub A raised to 3, and C sub B raised to 2. Okay? Now, so we write the rate law for the elementary liquid phase reaction solely in terms of conversion, and RA is a function of X. So the feed to the batch reactor where this reaction is happening or facilitated is equimolar in A and B. So meaning the concentration of A and B that enters our reactor are said to be equal. So equimolar or equal molar. So they have the same concentration in the value of 2 mole per decimeter cube. And you're given the rate constant here. So your rate constant here has the unit mole for amount of material, decimeter cube for the volume, and second for the time. So as for the answer for the rate law, this is it. If we're going to represent the rate law like this, class, okay? But if it's in terms of conversion, I will just answer this when I have already discussed conversion, because if I will introduce the XA now in here, then that will complicate probably to you. That will be complicated to you. So I will just represent the rate law in terms of concentrations for now. Later on, you will know as we go along how we convert from concentrations to conversions. Okay, so letter B, liquid phase. So when we speak of liquid phase, class, you have to understand that the volume is not going to change. Okay, let me repeat and emphasize this. For liquid phase reactions, so you could see here it's liquid phase. Okay? The volume of the system inside the reactor rather will not change. Or is not going to change. So it's a liquid phase reaction, and as such, your volume initial will be the same as the volume final. And that is the volume when your species have already reacted or there has already been conversion. Okay, so we'll just answer for now rate law in that form. Any questions? Okay, let me proceed. So remember, when we speak of rate law, let me go back to that slide. The rate law is something like this, a very simple representation of the rate law. Why am I emphasizing this? Because we also have what we call the rate equation. I think I have discussed this as well when we were talking, when I was discussing module 1. When you speak of equation, it has to be a differential equation, and it requires the presence of a derivative. In all cases, in most cases, this derivative is in terms of the rate of change of the number of moles of a particular species. So let's say, for example, we want the rate in terms of species A, and A is a reactant, as you could see in here. It's single phase. So this could be a liquid reaction. This could also be a gaseous reaction because it's single phase. So we write the rate in the most common way in which we represent it in here. We write the rate equation in terms of the volume of the system. If you recall our discussion in Module 1, there are, I think, 5 ways of expressing rates. It could be in terms of the volume of the system, in terms of the surface area when you have a two-phase system. That is the uh, interfacial area between your system, in terms of the mass of the solid, in terms of the surface area of the solid, or in terms of the volume of the reactor if the volume of the system is not equal to the volume of the reactor. So there are 5 ways, but the one that you are seeing here is the most common way of expressing the rate equation. Now you could see here in your rate that you have the unit mole of A per cubic meter per second. So mole for moles, cubic meter for volume, and second for time. So the amount of A disappearing per unit volume per unit time. So note, rate of consumption or formation of a species is an intensive measure. Anybody here who can tell me what do we mean by an intensive measure? The rate of a reacting species or a species that is being produced is an intensive measure. What do we mean by this? Intensive. It's a fundamental concept that was learned or discussed in Chem 1. The opposite is extensive. So when you speak of intensive property, extensive property, it's the same thing as is being referred in here. So what do we mean when we say it's an intensive measure? It's not an extensive measure. So the rate, whether it's consumption or formation, is an intensive measure. What do we mean by that? Can I ask anybody? Anybody? Intensive. What do you mean by intensive? Um, what do we mean by intensive measure, Fritz? Intensive measure. Fritz, are you there? Is Fritz with us? Do you have your, let me check. Do you have your, you don't have your mic on, Fritz? You can write on the chat box.
Yes.
Okay. Whenever we have the discussion, I ask you a question and there seems to be no response, you can still respond actually in the chat box. I will remove you from the room. Okay? Okay. What about via? What do you mean with intensive measure?
Hello, Miss.
Yes.
Um, Independent siya, Miss, sa amount ng substance.
Very good. Very good, Via. So that's it. So being an intensive measure, rate being an intensive measure, meaning whether we measure the rate based on a gallon of our system or we measure the rate based on just a liter of that system, the same rate will be able to measure because it's not dependent on the amount of substance or material. Okay? That it's not dependent on the amount of the system in the case of kinetics that we have. So it's intensive. Okay, that's very good, Via. Now we move on. So in here, in the next slide, you have another note. rate of reaction is influenced by the composition. So composition has something to do with concentration, and energy. Energy has something to do with, of course, the temperature. The higher the temperature, the greater the amount of energy of our material. And as such, you could see that in the right side of our rate of reaction, we have the temperature-dependent term, which is our K, and our concentration-dependent term, which is the C. Now, energy in here is the random kinetic energy of molecules or the light intensity within the system, which will affect the bond energy between atoms. Even the magnetic field intensity, if such applies. Now, but in here, at the end of it all, we are focusing on the effect of temperature on the rate of reaction. Of course, it will have a great deal of effect on the rate of reaction because our R sub A is dependent on the K, which is dependent on the temperature. So you can see here, rate is a function of the temperature-dependent term and the concentration-dependent term. In here, we have K, C sub A raised to A, where A is the reaction order. This A that we have is the exponent of the C sub A, where capital A here is the species that was used to, or it is the basis in which we determine the rate of the reaction, used as a basis. Now, in the last part of the equal sign here, you could see that your K was changed now into its Arrhenius equivalent equation. So you can see now that I have changed in here the frequency factor, the A, the capital letter A. Let me check here. It's in here. Let me go back. Okay, so you have here the capital letter A. In here is the frequency factor, and we have changed it. I have changed it to K sub O already. To K sub O. So you can see here it was changed to K sub O. Okay. Now, the other things that appear here in your final set of terms in the right side of your rate expression are defined in here. Now, you could see that your K, your temperature-dependent term, your rate constant will have a unit of mole per cubic meter raised to 1 minus A, where A is the reaction order, whatever is that order. It could be 1, it could be 2, it could be 3, it could be 1/2. So dependent on that. And S is raised to -1. Class, you have to remember this because I have a problem with some students not knowing how to write the set of units of the rate constant, even if they are even in the graduating years. If I will require them to reflect the set of units for the rate constant, they don't know because they forgot this particular formula. So the formula, take a look at it, is the unit for the concentration. So in this case, it's mole per cubic meter raised to 1 minus A, whatever A is, times S raised to -1. Now we go to, we're done with the temperature dependent term in here, which is our Arrhenius equation. And we go now to the concentration dependent term. So this depends on the type of reaction, which is also in turn dependent on the form and the number of kinetic equations used to describe the progress of the reaction. Though the number of kinetic equations used to describe the progress of the reaction has something to do with the reaction mechanism. So the mechanism really has a great role in the proper way of writing the concentration dependent term. If I will simplify it, class, the mechanism tells you the correct order of your reaction. Whether it's just a simple concentration of one species or several species, it's the mechanism that tells you that your rate law should have 2 for species A as its exponent, or let's say 3 for species B as its exponent. So this is, you will learn this later on when we do to proving or correlating the order of the reaction or the overall order of the reaction in terms of the series of reaction that reflects the steps that your species has to go through for it to form the product or products of your reaction. Now, the temperature in determining the order of the reaction must be held constant. So it's actually in our third module. When we determine the order of the reaction based on, let's say, a set of empirical data or a given data, it is on the major assumption class that the temperature is constant all throughout the manner of determining the behavior of the concentration of your species. So meaning in the process of determining how the concentration changes, the temperature has to be kept constant. That's how simple it is. So, or it is assumed to be constant throughout the reaction and when determining the concentration dependent term of the rate equation. The concentration dependent term is greatly dependent on the N, because anyway, we know what appears in our rate. It's always the concentration of a reacting species or species in this case in which I have written because there are 2 already. But as to this order, it depends on this one, the number of kinetic equations used to determine the progress of the reaction, or it depends on the empirical data that was provided by the problem. Okay? Any questions? Any questions?
None, Miss.
Okay, so I will proceed. Now, so again, the temperature dependent term is the rate constant K and its units are based on this. Okay, the time unit is raised to -1 and the concentration unit or units rather is raised to 1 minus n. Excuse me, class, give me 2 minutes. Let me share again my screen, class, ha? Can you see my screen, class, for reaction rate constant?
Yes.
Okay. So if we determine the rate constant in terms of T sub O, and normally we use the subscript T sub O for initial temperature, of course it follows that the T here that appears in the formula of Arrhenius on the right side of the equation will also be T sub O. Now at any temperature T, you will have to change, of course, the T to T. So actually, when we speak of T only without the subscript O, it means any particular time. O always represents initial temperature. If we take the ratio, if we take the ratio of the two, we'll have this one. So K sub T is equal to K sub T sub O, E raised to E over R raised to. So you have these two. Now, why do we come about with this particular equation? Anybody who understands why after these two equations that you have here, we have this? Do you understand why If we take the ratio of these two, we have this. Let me check. Okay. My question, class, is this. How did this particular equation in blue came about after taking the ratio of the two equations in white? That's my simple question. How did this came about? Because this particular equation we will use later on in determining rate constants in terms of data given to us for two different rate constants at different temperatures. Anybody? Let me check. Albert, John Albert Villarosa. John Albert, are you there? Okay, sige. Love Miss. Okay. You don't have your microphone, John. Wala ka microphone. Yes, Miss, the business subo ang data. Okay. Okay, I will ask another one. John Patrick Tagle, was it right when John Albert said that if you take the log of the two equations in white, you will come up with the one in blue underneath here, the one that I'm pointing to. Patrick Tagle. Did we do the log? Do you agree with John? Yes, miss, I think. Okay, what about, so this is the last person that I'm going to ask. Ezra. Ezra.
Yes.
Okay, what's your, how did this blue equation came about using the first two white equations?
Ang first equation is gin-transpose, miss, para mag-equal sa A. Tapos yung substitute ang A sa second equation.
You mean, wait, you mean you took the A from the first equation and then substituted it in here? Is that what you mean?
Yes, yes, I think. Not sure.
Okay. What about Drexel? Drexel, are you there? Drexel.
Yes, miss.
How did this blue equation came about from the first two equations, the one in white, shaded in white? How did it came about?
Ano, miss, for the first equation, miss, we solve, miss, we transfer, miss, ang t sub 0 sa other side, miss. For the first equation, miss. And then we plug in AE negative E over R, miss, sa second equation.
Okay. Sige, I will explain to you. The blue equation that you are seeing here, it's stated here. Okay, let me underline. Taking the ratio to obtain. So coming from that, it says it took the ratio of these two. Now you can see if it took the ratio of these two, the left side will be, let's say if we'll have this one on top and this one below, you will have K sub T over K sub T sub O in here. It's equal to AE raised to negative E over RT minus, or rather divided by AE raised to negative E over RTO. Now, since you have A in both of this, they will just cancel each other. So what I'm trying to say is this. Okay, let me annotate. You have K T over K sub T sub O. Since you're taking the ratio, the term here is ratio, you copy this one. So AE E and then you have isn't it that we can cancel this two? Now I can write KT equal to, so you have, isn't it that we have in the rules of exponents that when we divide, we can represent it as 1, and you have negative E over R, and you have 1 over T minus 1 over T, 1 minus T sub O. And since it's written here to be positive, you get this one negative and you interchange this two. So you have K sub T sub O equal to E raised to E over R. You have 1 over T sub 1 over 1. Okay? And then what else? This one goes here. You will have this. Do you get what the reason why I am emphasizing the manner of derivation here, my dear students? Because in here in kinetics, most of the time you will derive the equations that you are working on. It's important that you have a good mathematical understanding of why the equations that were presented to you here in the slide as already a given and final equation, why they are presented that way or how they came about. So the reason is this is the one that I'm sharing with you now. Okay? Although there are several ways of killing a cat, as they say, you have to understand, I will emphasize this over and over again, that you have to learn to do things, derive equations here in kinetics on your own and understand them. Otherwise, you will be stuck. You will be stuck with the equation that you are to work on, and you will not even go to the part in which you are going to substitute the actual data that is provided in the problem. If I may say, my dear student, like 40 to 50% of the solution of the majority of the problems that you are working on is heavily anchored on deriving the equation or the formula. So it's very important that you understand how the equations came about, especially with the equations with the derivations that are given in your book by Levenspiel. I hope that you will spend time on reading the equations, the derivations that are presented in level speed. That way, later on, when you are the one left to do your own interpretation of the problem, you will know how it came about. Majority of the equations class that are provided in kinetics are shall I say, applicable only on the scenario or on the condition that is stated in the problem. If that condition or scenario changes, your equation changes and you will be the one to derive it. So if you don't understand any of the derivation that happened, you will really be lost. Now, so I am asking you this last question. Do you understand now why I have to ask the question to you, how this blue equation came about? Do you understand why this is the answer? So this K sub T sub O here can simply be cross-multiplied here on the other side and amo na ni siya ang magwa. So you have to always go back to the, let's say, kung ano magid bala ang instruction ni ginhatag sa problem, kung ano ang fundamental, balikan yung gid na siya. So kung ang ginahambalang man diri, you take the ratio, then take it from that. Take the ratio. So when you take the ratio, this will be the corresponding expression. Okay, now you have here energy content on the vertical axis and you have here temperature on the horizontal axis. If the activation energy that is written here on the right side is depicted in this very simple illustration, you can see that that's the amount of energy, is E here. This is the amount of energy necessary. That way, your reacting species is in the form that it would be ready, or it is already ready to react with another. So without this activation energy, your reacting species won't be able to be rendered ready for reaction. So it has to be rich. As defined in here, defined as the energy that must be overcome in order for the chemical reaction to occur. So this is your activation energy. And this energy is a function of temperature. So you have energy here on the vertical axis and you have temperature here on the horizontal axis. Okay? Now, let me clear my screen here. I will just finish this part of the slide, then I will dismiss the class. So why is there an activation energy? So the molecules need energy to distort or stretch their bonds in order to break them and to thus form new bonds. As the reacting molecules clump together, they must overcome both steric and electron repulsion forces in order to react. So they need this energy. That way they'll be able to break the existing bonds and form new ones. Without the breaking of existing bonds, there won't be any new bonds that will be formed. And this activation energy is present in your Arrhenius equation. Okay? On a final note, when we increase the temperature, we increase the kinetic energy of the reactant molecules, which can in turn be transferred to internal energy to increase the stretching and bending of the bonds, causing them to be in an activated state, vulnerable to bond breaking, and then, of course, they will be able to react. Activation energy is that minimum amount of energy required to initiate a chemical reaction. So this is the simplest definition of the activation energy. You remember a while ago the derivation that I have shown to you? From that particular derivation class, you will be able to get another set of relationships here. And this is also very fundamental and important in kinetics. So now you could see the LNs in here. So if I may ask, why LNs? Why the LN in here? Why do you think the LN appeared in this box set of equation here? Na nag-appear na da siya. What's the purpose of the LN? The purpose of the LN?
To cancel E, miss.
Oh, very good. So, para madula ang E. So, prior to canceling the E, what is done? You will have K over K sub O equal to E raised to negative E over RT. You take the ln of both sides. That's the one Rexa was saying. So, you get rid of the E. Now, we did not, you notice class, we did not only limit it to ratio of ln of K and K sub O, the rate constant and the pre-exponential factor here. But rather, we can also change this ratio of K into and K sub O into two different Ks. Two different reaction constants at two different temperatures. So you can see in here, ln of K sub 2 over K sub 1. We got rid of the E already. So, amo na lang yung nabilin. E over R, ratio of, rather, times 1 over T sub 1 minus 1 over T sub 2. The reason why you have T sub 1 as the first subscript here appearing for your T and not T sub 2, it's because we made the E over R positive. In here, in the original equation, we had it negative. So, if we make it positive, then it will interchange. Okay, so the main relationship between case and temperature is only this. The very simple relationship, K sub 1 over K sub 2 is equal to E over R times 1 over T sub 2 minus 1 over T sub 1. If it's 1 here, it should be 2 here. If it's 2 here, it should be 1 here. Because we made the ratio of E over R positive rather than negative as written in here. But we extend the ratio of the ln of K's to the ln of time. This small t here is time. So the ratio of the two times. So meaning this is the time for this corresponding rate constant. This is the time for this corresponding rate constant. In terms of rate, we can also do that. So kung nag-K sub 2 over K sub 1 kita dire, ang ln natin sa rates R sub 2 over R sub 1. So the same siya. But in terms of time, so if it's 1 here, it's also 1 in here. If it's 2, it's also 2 in here. This set of equations, so this could be equated to this to this, or this to this. This set of equation will prove very useful if you're given a set of data that relates time with temperature, the amount of time a reaction will reach a certain degree of completion based on a particular temperature, and another time for another temperature. So it could be this and this. Or it could be rate constant in terms of temperature or rate in terms of temperature. Now, we use this equation depending on the kind of data that is provided in the problem. So, this particular equation is an extension of the basic fundamental equation of Arrhenius, which is K equal to K sub O, E raised to negative E over RT. Okay, so remember this formula. You will have problems wherein you can apply this formula later on. Now, when we meet each other on Wednesday, I will finish the set of slides with sample problems that are needed to be discussed as well, especially in terms of the application of this set of equations. So please do read ahead. That way you will have a knowledge already of what is to be discussed on Wednesday, because it's a given that after Wednesday, during your dry lab, you will solve the problems that were given in the problem set. Okay, so the next part in here, class, is already generalizations. Let me clear, by the way, what I have written here. The next part in here will be the plot of the Arrhenius equations at high activation energy and low activation energy, and the different generalizations that we can make out of it. So we will discuss it next meeting, and that would be on Wednesday. Do you have any questions for now? So there's none. Okay, so let me stop sharing.